All right. Welcome to this presentation on wind farm analysis with RETScreen Expert. I'm Michael Ross. I'll be the presenter for today. I should start off by acknowledging that this webinar is provided at the request of and with the support of Natural Resources Canada. So a big thank you to them, particularly because that permits me to send you at the conclusion of this webinar a 30-day subscription to RETScreen Expert. So if you're not currently subscribed to the tool, this subscription will allow you to unlock the full functionality of the software for a 30-day period. Use the software to see if you like it or if it's useful for you. And then at the end of the 30-day period, extend the subscription if you wish. For today's presentation, I have a few things planned. The first will just be a reasonably quick introduction to RETScreen's capabilities. So those of you who are not familiar with the software will get to see an overview of what is included in RETScreen. Then I'll talk a little bit about one specific type of project that can be studied with RETScreen, and that's pre-feasibility analysis for wind farms, so utility scale wind projects. And after talking about that for a bit, in theory, we'll do it in practice by looking at a particular pre-feasibility analysis of a wind farm in British Columbia, Canada, a proposed wind farm. And finally, there'll be a session at the end for questions. So if any questions you might have, if you could save them for that time, then that would be great. We can open the floor then for questions. I should mention that this webinar is being recorded. I'll just verify that it's being recorded. Let's see. Yes, it is being recorded. Good. And that means that anything you bring to the questions will be part of the recording. So just be aware of that. But it also means that should you wish to review this at a later date, there will be, I believe, a link to it on the RETScreen's YouTube channel. So you should be able to see this later on if you wish to refer back to it. So RETScreen software capabilities. The first one of these is benchmarking. So this is when you particularly useful for energy efficiency projects as opposed to energy production projects like a wind farm. You might be starting out with a facility, you have very little information about it, and you want to situate yourself in terms of how much energy would I expect this facility to consume. So to get a first estimate or approximation of that, you can look at the energy consumption of similar facilities. And then that provides a first understanding of what you may be dealing with at your facility. This can also be applied to energy generation projects. So for example, for electric generation in photovoltaics or in wind, you could look at a benchmark that gives levelized cost of electricity. So we'll see that in a bit. So an energy production cost. If you want to move beyond general comparisons with other projects elsewhere in the world and look at the particularities of your project, you can do feasibility analysis with RETScreen. So here a project has been proposed and you want to assess whether it's technically and financially viable. And this is what we're going to be looking at mainly today. Another capability of the software is performance analysis. So to this point, you're probably talking about a project that has not yet been built. With performance analysis, you are always talking about a project that has already been built and for which you are collecting monitored data on an ongoing basis. And you want to analyze this monitored data to determine whether the project is functioning according to your expectations, whether it's achieved, for example, energy savings that you expected or energy production that you modeled. And RETScreen can help you do that. The fourth capability in the RETScreen software deals with aggregating energy information from groups of projects. So in those first three capabilities, we're looking at a single project at a time, individual projects. With portfolio analysis, we're looking at groups of projects. This may be particularly useful for people who are managing a large number of facilities. So for instance, someone who's managing a large number of electrical generating assets, or someone who's perhaps responsible for managing all the buildings on a university campus. This might be useful for them to group different facilities together and see how their energy performance evolves over time. The fifth capability, I've called it a capability, it's not really a capability, but characteristic of RETScreen is that it includes a lot of data in built-in databases and a lot of help, particularly useful for people who are new to these technologies or these projects. They may find that the help gives them an insight into what different parameters associated with these projects mean and what their influence is on these projects. So I think it's a great platform for learning about these technologies. And even if you choose not to use the benchmarking, feasibility, performance, or portfolio analysis, sometimes just having access to the data that's built into RETScreen can be helpful. So let's take a very quick kind of quick overview of RETScreen here by looking at the software for a particular project. So I'm assuming that you have not seen RETScreen before. If you have seen it, then I'll just sit back, relax, and we'll get to the wind farm in about 20 minutes. This is how RETScreen looks when you open the software. You can see across the top there are different tabs. We will be visiting each of those tabs just to quickly see what's in them. But we start off on the File tab here. And the File tab has much of the functionality to expect from an application's File tab, right? We can open and close analyses here, and we can save our analysis. So that's all the type of functionality we'd expect. It does link to a few other things that we should mention here. On the left, there's a settings page here. And if I click on that, I see that I can configure many things like the language of the analysis, right? Many different languages are built into RETScreen, the currency, the unit system, number formats, etc. And there are even further additional settings that are only available in the professional mode. That is when you have a subscription to RETScreen. So if you don't have a subscription to RETScreen, there's some basic functionality provided in the software, but if you have the subscription, then you get more functionality. So the settings page is accessible here. I should also point out that here there's a help page. This is where you can check for RETScreen updates, but it's also where you can access different forms of help for RETScreen. One place you can access them. In particular, I'd like to draw your attention to the engineering e-textbook here. If you click on this, you can access a very significant description of the algorithms that are used in RETScreen. So for many of the technologies, it does not need to be treated as a black box. For many of the technologies, you can use this to look and see what it's doing, if that should be something of interest to you. For many engineers, they like to have that. There's also here subscription. So as I mentioned earlier, at the conclusion of this webinar, attendees will receive a software key. You can apply this software key to an installed version of RETScreen through this subscribe part of the File tab here. So if you scroll down, you see Add Software Key here. This is where you click to apply the software key that you have. So that's kind of the functionality over on the left-hand side here. In the center part here, we have different ways of starting your analysis. And I'm going to get to those in just one second. Before I do that, I'm going to mention over here on the right, there's some functionality. I'm not going to go through all of it, but I do want to draw your attention to one piece of functionality in particular, which is this link to the RETScreen's e-learning channel. You will see this icon in many different places in RETScreen. If you click on it, it takes you to training videos that have been prepared in the past relevant to the current location that you're at within the software. But if you click it here, it just opens the RETScreen YouTube channel. So you can see there's a YouTube channel with a lot of different languages, a lot of different videos in multiple languages. This is the English channel, but there's also French, Spanish, and Chinese. So a lot of different videos available to help you understand how to use RETScreen. Going back to the software here, I mentioned that we have a number of different ways to start your project. When we do our wind feasibility study, I'm going to start with a blank project. So no assumptions already given in the inputs to RETScreen. And I can do that by clicking here. It says analysis type blank project feasibility. That's how we'll start that. I could also start a benchmark analysis or performance analysis here, or an analysis that includes all these elements. So these are possible here. I can also access, files that I've saved in the past through this, My Files. It does the same thing as open here. There's also a bank of case studies and templates. So if you can find a project in here that resembles the type of project that you want to work on, you might take a look at this to see how it can be worked out in RETScreen. So that's helpful sometimes if you want to build on an existing analysis. I mentioned that RETScreen is capable of portfolio analysis. We're probably not going to have time to look at that today, but if you're interested in portfolio analysis, this is where you can access it. And there are two built-in examples here. We can see from this graphic here that a portfolio analysis contains multiple individual RETScreen analyses from potentially different facilities, which can then be added to over time. And then within the portfolio analysis, you can aggregate these facilities in different ways according to whatever criteria you want to apply and see how their energy performance evolves over time. Over on the right, we have some buttons here that will open example projects. So when you're learning how to use RETScreen, this can be helpful. So for instance, we might be interested in looking at a power plant project. Before I do that, I'm just going to mention the one I skipped here, which is the Virtual Energy Analyzer. One way to start your project would be to use this Virtual Energy Analyzer. By clicking on it, you can configure RETScreen to search for the type of project you're looking for. So for instance, for a wind farm feasibility study, we'd want to do a power plant using wind turbines. And let's say it was a 100 megawatt project. We'd pick 100 megawatts here if it was an onshore project. And then we could situate the facility by, telling it where it is. So if it's somewhere in Texas, say, I could say, click on here. It takes me somewhere to the center of Texas, and I could put my project there. And what that would do is it would open an archetype, meaning an example project that would be a wind turbine project of 100 megawatts. That doesn't mean that all the inputs that it's using are going to be perfectly suited to my project, but it does provide some defaults that are at least somewhat tailored to my type of project. So that's another way to start things. I'm not going to demonstrate that here, but you should be aware of that. Rather, for right now, I want to show you a fully worked out example, which I'm going to access through this. Once we've quickly looked at this overview, I'm going to return the presentation and eventually come back to doing a feasibility study starting with a blank analysis. So by clicking on this, I'm opening a fully worked out project in RETScreen. What do I mean by that? It will have data and inputs filled out in all of the tabs of RETScreen. And by all the tabs, I mean all these tabs across the top. So let's look at these different tabs. So the first one, which I find myself in now, is the location tab. What this is doing is telling RETScreen where my facility is located. So I've got the latitude and longitude here, as well as the elevation of the facility, and where RETScreen is getting climate data from. So the climate database is shown here. This is taken from this location here. The climate database contains monthly average values for these parameters that you can see here. These are the monthly average values, and then these the annual average value across here. And you'll note for every column here and every row here, there's a source indicated, which may be either ground, NASA, or user-defined. So ground indicates it's a station on the ground where these measurements are being taken. NASA indicates that these are measurements that are derived from satellite-based measurement platforms. So this will be important when we're doing our wind feasibility study, so I'll return to that point. At the bottom, there's a graphic where we can show any two of these parameters as they evolve over the course of the year. That's the facility location page. The facility page itself is where we configure the RETScreen analysis to be the type of analysis we want. What do I mean by that? Well, first, we indicate here what type of analysis we're doing, whether it's a benchmark, feasibility, performance, or all three of those. And here we have all three suggested. So we'll see those three different elements in this single analysis here. We also give the facility type, the technology type, the description, who this has been prepared for, etc. So we'll fill that out. We can change the image to an image of our project or our proposed project if we wish. And at the bottom, we come to the first of RETScreen's broad capabilities, that being benchmarking. So here we have a benchmark indicated in this green dotted line, which is apparently 9 cents a kilowatt hour. That's an energy production cost. Energy production cost is a term that also goes under the rubric levelized cost of electricity. It is a way of estimating or approximating the average net cost to provide power using a technology. And these bars here compare different technologies in terms of their minimum and maximum energy production cost, or their minimum and maximum levelized cost of electricity. And in blue here, darker blue, we see that for wind turbines, because that's the technology that we have selected here. So it's showing us what's particularly relevant for wind turbines here. And we've got a benchmark it's come from somewhere. I mean, I can actually just modify this and say, well, let's say I am expecting the levelized cost of electricity for my project to be 10 cents a kilowatt hour here. So you can put in 10 cents a kilowatt hour. And I should mention that unless otherwise stated here, dollars in cents are Canadian dollars and cents, not American dollars and cents. So adjust your expectations based on that. But I can compare this benchmark to the ranges that I might expect, minimum to maximum energy production costs for these different technologies. Obviously, these are really wide ranges. If you're interested how these ranges were calculated, you can click on the benchmark database here and see the assumptions. So there's some common assumptions for all of the technologies, like the inflation rate, the discount rate, the project life, etc. And then there are some assumptions that vary from technology to technology that govern the range of these bars that you saw here. So this is where the benchmark is coming from. Sometimes I think it can be confusing to have the benchmark here when you're doing a feasibility or performance analysis, because it can be tempting to expect that there is some sort of link between your benchmark analysis and your feasibility study or your performance analysis. And there's essentially no link. There's a tenuous link that we'll see, but it's one that I can choose to include or not. So the fact that we have a benchmark indicated here doesn't in any way influence what happens in our feasibility analysis or reflect what's happening in our performance analysis. So basically, this stands alone as a piece of information that you can choose to consult or not if you find it useful or not. The next of these tabs is the energy tab. And from an engineering perspective, this is kind of the most interesting tab, because it's where you describe the energy performance of your system. So there's a menu bar along here, which if you're building out your system, you tend to follow from left to right. So the first thing here is electricity and fuels. We could also access that by clicking on electricity and fuels here in the navigation pane. This takes us to a list of fuels that are available at our site. You can add fuels by clicking here. By default, there's always some fuel available. And this being a wind project, that may be a little bit confusing, because obviously we don't need to have any fuel for a wind project, but you can just choose to ignore it. So for instance, I can just eliminate that. It's equivalent to saying, just because there's a natural gas line running down the street doesn't mean you have to hook up to it when you build a turbine on your property, place a turbine on your property, or a photovoltaic system. You're not obliged to use it. Here, the second part here is the electricity export rate. Don't let export throw you. This is simply saying what value is being accorded a kilowatt hour of generation from our project. So here, by default, the value is a little over 10 cents a kilowatt hour. That's the value we're going to accord to our project when we select this electricity rate. You can add multiple rates to test different hypotheses by clicking on here, right? You can have multiple rates, but we're just going to have one rate here to keep things simple. Now, this example already has a wind turbine there built in. So we can see here's the model for the wind turbine. At the top here, and I will just quickly skim over this because this is where we're going to focus when we do the feasibility analysis. We have some information about our wind resource. Then we have some information mainly about our turbine, which includes a turbine power curve. Power curve tells us for the equipment we've chosen, for the turbine we've chosen, how does a particular wind speed translate into a particular level of power output. Then we have some loss factors here. Finally, we specify the initial costs, so the costs to build the project, and the O&M costs, which are the costs to operate and maintain the project annually after it's been built. And based on that, RETScreen gives us here this very important summary of the characteristics of our project. The first of these is the capacity factor, which is the average output of our project expressed as a percentage of the nameplate capacity. So for a 100 megawatt project, right, which this is, it's let's see, 101 megawatts. So 101 megawatts for that size project. If we have this 31% capacity factor, it means that on average, we're putting out 31 megawatts, right? 31% of 100 megawatts is 31 megawatts. So that's an important output. We also then have the electricity being generated and provided to the grid that on an annual basis, so that's 274 gigawatt hours per year, and the electricity export revenue, meaning how much are we earning by selling this electricity at 10 cents a kilowatt hour. And it works out to about $28 million per year. And we can compare that with the initial costs here of 202 million and the O&M costs of under 4 million a year. So this is the energy model. We'll spend more time with this tab when we do our own feasibility analysis. I'd just like to move on to the cost analysis here. Cost analysis, by default, is what's the most simplified analysis, is signified by level 1 here, which just copies over the annual and initial costs found here, right? 202 million and 3.6 million are carried over here. 202 million, 3.6 million here. We could add elements, right, by adding them in here, and we can develop a much more detailed cost analysis. We'll see that a bit more when we do the feasibility study. Moving on here to the emissions analysis, we see that for this particular analysis, the emission savings for this project or the emissions reduction are 0. Why? Because it's on a grid which has an emissions factor of 0, meaning in Quebec, the average emissions associated with generating a megawatt hour of electricity are 0 tons. However, in other jurisdictions, that would not be the case, right? So for instance, if we put this next door in Ontario, which has a fairly clean grid, but not as clean, you'd see that the emissions factor there is about 45 kilograms of CO2 equivalent per megawatt hour generated. And in that case, assuming that our wind turbines have no emissions associated with them, at least during operation, not during construction, that would result in annual savings of 12,000 tons of CO2. If we thought we could monetize that, we could accord it a value here in dollars per ton. but this is a fairly small emissions reduction, so maybe we wouldn't be able to do that. On the other hand, someone might say, well, listen, you're generating this power in the province of Quebec, which has a very clean hydro grid, but maybe you're going to sell that project or sell that power across a border. Perhaps you're shipping most of that power down to the New England states. So in that case, you might choose to look at, the emissions in, say, Massachusetts. And you'd see then the gross annual GHG emissions reductions is much more significant, and it might make sense to monetize those. Another way to look at that would be to do a level 2 or level 3 analysis. Under these methods, you're no longer giving an average emissions factor, right? This is an average emissions factor for generation on the grid currently in Massachusetts. Rather, here you can specify a mix of generation sources or assets that you think are going to be offset by your wind farm. So if you thought that your wind farm was going to reduce uniquely natural gas-fired generation, then this is an emissions factor you could use based on these assumptions. So this is another way to do emissions analyses with RETScreen. For now, we will just leave that where it was to begin with, which is Canada in the province of Quebec. Finally, we can tie together these elements of our feasibility analysis on the finance page. And here we have the finance page. You can see once again, there's a level 1 and 2 here. It's on level 2 right now, but if I skip back to level 1, I'll see the same results in a bit simplified form. So there's a few financial parameters specified here, notably the project life being 20 years, the inflation rate, and the debt ratio. So 70% of the initial costs are being borrowed from a lending institution. Those will be repaid at a 7% interest rate over 15 years. That's what this is signifying. So 70% of this number is coming from a bank and needs to be paid back with interest. The remaining 30% comes from equity investors, and they are going to see a return on their money. And we see the return that they achieve on their money. It's an internal rate of return on the equity portion of 20.2%. So it's a very profitable project, right? Much better than investing in the stock market, generally speaking. So this is a simplified view of the financial analysis. We have a nice graph here which shows the cumulative cash flows, meaning the initial outlay is the initial roughly 70 million equity investment, right? 30% of 202 million is about 70 million here, 60 million apparently. And then out of the electricity generation revenues, over time, our initial equity investment is paid back such that over the 20-year lifetime of the project, these are the cumulative cash flows summing from one year to the next, the positive and negative cash flows. If we want to see these financial viability parameters augmented by some other financial viability parameters, we can go to the level 2 analysis. It gives us the same IRR that we are looking at there, but it gives us additional information as well. For instance, it gives us the net present value for this project, given that the discount rate is 9%. So you can play with those values. Another nice thing it does comparing the two is here the inflation rate is 2%, and that's being applied to all future expenditures and revenues. So both your electricity revenues and your O&M expenditures are all inflating at 2%. And if you thought those should inflate at different rates, you can go to a level 2 analysis and choose an inflation rate for your O&M and an electricity export escalation rate for your electricity costs. So a little bit more detail here in a level 2 analysis. Now, here we have 20.2% as being the internal rate of return for our project. And obviously, this is based on a number of very significant assumptions, which probably aren't going to be all perfectly correct. So we can investigate the sensitivity of our analysis to potential errors or discrepancies in our individual parameters by going to the risk page here. The risk page has two components, a sensitivity analysis here at the top and a risk analysis here at the bottom. So the sensitivity analysis here allows us to look at simultaneous variation in two parameters or even just variation in a single parameter. So for example, if I was interested in the net present value, say here, and I wanted to see what the impact of the initial costs is on the net present value, I could just do this where I say, show me the impact on the net present value of initial costs being plus or minus 25% compared with the current value specified for the initial costs, right? Currently, we have a project that has an initial cost of 202 million. So that's the central value here. If we add 25%, it works out to, if we initial costs, yeah, this is actually reversed. If they go up by 25%, it's no, sorry, I'm wrong. If we go up by 25%, it's 253 million. If we go down by 25%, it's 152 million. This is the impact on the net present value. So that's varying one parameter. We can see the sensitivity of the net present value to this one parameter. We can look at that in combination with another parameter. For instance, if we look at the electricity exported to the grid, we can see combinations of these two, the sensitivity of the net present value to these. So we can explore these for, multiple combinations of variables. However, we might be interested in seeing what goes on when all input parameters maybe are having a little bit of error associated with them. And we can look at that with the risk analysis here. So if we're once again looking at, say, the net present value here and looking at 2,000 estimates of this based on the Monte Carlo simulation. So I'll explain that. We have these 7 potential inputs that we think there may be some error associated with. That is, we're not sure that the values we specified are perfectly accurate. So we give them each a range and say they're going to vary within plus or minus whatever range we specified. Here it starts out all at plus or minus 25%. So that gives this range for the initial costs. And then we allow all of these parameters to simultaneously vary in a random way between these minimum maximum values. And we choose 2,000 sets of these parameters varying between these minimum and maximum values. And then we see what that results in terms of a distribution of outcomes for the net present value. So here's the distribution of outcomes. We see that most of them are positive, which is good. That means most of the time, if we allow these parameters to vary within these ranges, the result is a positive net present value or a profitable project. There are, however, a small percentage of cases where we have a particularly bad outcome in multiple parameters that leads to a negative net present value and therefore a project that's not profitable. So this gets away from the notion of looking at a project as a single financial outcome as 20.2% and recognizes that really at this stage, we cannot be sure that we're going to have an internal rate of return of exactly 20.2%. But on the risk analysis, we can try and get a sense for what the range of potential values are and what are likely values. And we see in most cases, this would be a profitable project given the assumptions that we've made here. The other way this can be useful is to help us assess which parameters have the biggest impact on the net present value. And we see here that it's actually the amount of electricity being exported to the grid that's most significant. considerably more significant than the initial cost, which is somewhat surprising, and much more significant than, say, the debt ratio or the debt term, also somewhat surprising. So that's a risk analysis. Those tabs are dealing with the feasibility study. The next tabs are for the performance analysis. So if I go to data here, and let me just try and make this disappear. Yeah, there we go. On the data tab for performance analysis, we see this is collected. Sorry, I should put it here. We have each day's electricity generation for this project from starting on January 1st, 2016 through the end of December 2020. So we have all these daily electrical output, and we also have in this table weather output. So why do we have weather output? We have weather output because we expect the wind speed we measure each day to have an influence over the electricity production that we see here. So if we see the electricity production going up and down, that could be indicative of a problem with our project. If we see, for example, the electricity production drop down from one day to the next, or it could simply indicate that the wind was less strong that day. So in order to assess whether some underlying problem or deterioration in our wind farm, we really have to remove the impact of the changing wind speed. And we're going to do this by taking this table and carrying it over to the analytics page here, where we can generate some graphics and some analyses, some regression analyses. So the first thing we might look at here is the, let's see, the electricity production, which are these blue bars for 2016, 2017, 2018. And the purple line here indicates the wind speed. So we see, generally speaking, higher production is associated with a higher wind speed, as we would expect. So right there, there's some indication that things are okay. We have some other nice graphics that we can look at. We can look at a monthly bar graph for electricity production in 2019 and 2020. We see there's quite a bit of variation from one year to the next. We can look at a climate data graph here. So here we're looking at the wind speed in the blue bars here over the entire period. So every January, the average for every January in the period was 6.1, and we're comparing that to what is shown for January 2019 and January 2020. So this is just an example of 3 graphs you can use to examine what's going on in your system. Where things really get quite a bit more interesting, though, is when we do a regression analysis. So for instance, here, we do a regression analysis where we attempt to explain or predict the electricity generation of our turbine, our wind farm, over the course of a month by looking at the measured wind speed during that month, so the average measured wind speed. And we're doing this for a year, 2016. We use 12 values, that each of these values corresponds to 1 month in 2016. And we come up with a linear equation that predicts the electricity production in megawatt hours per day from our wind farm based on the wind speed, the average wind speed for the month. And we can see there's a pretty good linear correlation here. It's 96% coefficient of determination. That indicates it's really quite good. So having done that, we can then say, well, we have this model here that allows us to predict the electricity consumption of our wind farm based on the measured wind speed. This is based on 2016 data. If we run this forward into 2017, 2018, 2019 on an ongoing basis, we would expect that as long as the wind farm is functioning correctly, this model will continue to work to predict the output of the turbines. And if we see some deviation between what it predicts and what we actually measure, that indicates something strange is going on. So we can see that, for example, here in a measurement and verification chart. We kind of essentially calibrate the model on the 2016 data, and then after that, we compare the actual electricity consumption, or rather production in green, and the baseline, meaning the estimated production, estimated based on the equation that we generated here and our measurement of the wind speed, the monthly wind speed, and we can see there's a really close correspondence. Of course, it would be interesting to compare for each period the difference between these two, and we can see that in a control chart here, where we're looking in relative terms at the difference between the two. So we can see when there's a really significant difference between the two. An even more interesting way to look at that would perhaps be to sum the differences from one period to a next. So essentially to integrate the area between these curves and do a running integration of the area between these curves. Why is that interesting? Because it allows us to detect a small but persistent difference, indicating perhaps a slight degradation in performance that occurs, that persists over time. This will become apparent if we integrate the area between the curves. And that's shown in something called a Q sum or a cumulative sum of differences chart. And you can see that here. In the initial months, there's a significant drop here, indicating that the actual electricity prediction, the actual electricity output was much less than predicted. But then over time, it ramps back up. So things actually improved after a while. So you would want to investigate why there are these drop periods. I happen to notice that most of the time they happen in the first 4 months of the year. So you might want to find out what that's causing, what's causing that. But you might also want to find out, what went right. Why is there kind of generally an upward slope here compared with here? What was it that led to better than predicted performance, particularly through this period? So performance analysis allows you to identify these interesting phenomena, and then perhaps you can investigate them. Here on the report side of things, we can generate a feasibility report or performance analysis report. We can customize the report with the edit functions here. We can choose what we want to include or not include, and then export the report. And then also for getting our information out here on the custom page here, we have a kind of a custom view of different elements of our analyses that we can drag and drop in. We can choose what we want to include both for this feasibility analysis and for the performance analysis. So these are elements of our analyses that we find particularly interesting or important that we choose to drag into this page here. And then we can, export this in a number of different ways or just display it on a screen over time. So that's a quick overview, or perhaps not so quick overview of the RETScreen software. Let's return to the presentation and talk about applying this to wind farms. And we're in particular going to look at feasibility analysis. So the idea here is that someone, perhaps it's you, is proposing a clean energy project. In our case, it's going to be a wind farm. And you have to answer the question, is this a good idea? So what do we mean by good idea? How much energy does this project produce in the case of a wind farm, or save in the case of, say, an energy efficiency project? Is that going to be a profitable project? Is it going to make us richer in the long term? Or the equity investors, are they going to get richer in the long term? And distinct from that is how quickly will the equity investors get their investment back? This is slightly different from profitability, even though we tend to conflate the two, particularly here in North America. But you can have an investment which has a very quick return, but after it's returned its money, it doesn't generate a lot of revenues, and that doesn't necessarily make you richer in the long term. Will you be able to get financing for the project? We were just looking at a wind farm that was $202 million in initial costs. This is a lot of money. Most of us don't have that, and we're going to have to go to a financing institution. And they're going to look at our project in terms of, does the project generate sufficient revenues to ensure that they get paid back their principal and their interest? They don't really care whether the project is profitable. What they care about is getting their money back and their interest. So they're going to be looking at that, your project, and you should probably also, in preparation for that, look at that as part of your feasibility study. Also, greenhouse gases are at various times and for various projects very important considerations. So you'd want to include that as part of your pre-feasibility or feasibility analysis. So a feasibility analysis, say for a wind farm, is quite involved, right? You may have to install a number of different wind measurement towers and other like LiDAR on site, leave it there for a period of, say, at least a year, analyze that data very carefully, do a lot of other studies related to everything from foundations to environment and grid interconnection. That's all very expensive. But before you embark on that, you might want to do a very quick check to see whether your project is in the ballpark, and that's pre-feasibility analysis. So doing a very quick feasibility study, as much as possible, making use of data that you might already have available. And that's what we're going to be looking at today. So we just said that wind farm projects might be, $200 million or more, 200 million for a 100 megawatt project, say. Bigger projects will cost more. Obviously, for projects of this scale, you're not going to be using RETScreen to do the engineering for the project, and it won't be your sole financial analysis tool. There are specialized engineering and financial analysis tools for wind farm development. Obviously, projects of this scale are going to be dealt with very detailed and specialized pieces of software. But RETScreen can complement these tools. There is a role for RETScreen, I believe. First, in contrast to these tools, it can provide really rapid, easy initial analyses, which allow you to jump into a project and get some sense of what's going on without having the obligation to use a very detailed and heavy tool, something that requires a lot of expertise and a lot of input data. So already that's helpful. Furthermore, because it's easy to run and quick to run, it's great for doing what-if analysis to investigate, well, if this parameter changes, what is the overall impact on financial viability, greenhouse gas emissions, production of our project? And it's much easier to do that with a simple tool than it is with a fully detailed, in-depth tool. Now, obviously, the simplified tool can't do all types of what-if analysis, but you can bring results in from other more specialized tools into RETScreen, and then RETScreen can kind of provide a high-level overview of the main elements of your project. And I've seen this being done where developers obviously for wind farms are having their specialized tool, but parallel to that, they keep an updated RETScreen analysis, which helps them kind of get an overall idea of what's going on in their project without getting lost in the details of their specialized tools. Now, the other interesting thing is, because it's easy to use, you can use RETScreen to investigate claims made by others. We hear a lot of claims being made by both project proponents and detractors of renewable energy technologies. And you can test those claims using your own assumptions, using a tool like RETScreen. If someone claims that, this type of project is never going to be cost effective without government subsidies, or someone else claims they have a highly profitable project that's, kind of going to make you very, very rich, you can test those by setting up a RETScreen analysis and, putting in your own assumptions and seeing whether the claims are reasonable. And furthermore, the RETScreen analysis is a nice encapsulation of the project that you can share with people, including, those people that you want to discuss your project with, if someone's making a claim and you don't think their claim is right, do a RETScreen analysis. Send them your RETScreen analysis. Say, okay, this is why I disagree with you. Which of my assumptions do you not agree with? And they can change those assumptions if they can justify that. And it can really clarify where you differ in your analyses of the projects. I've personally found this very useful in helping a client who has requested proposals for a small hydro project. And each of the proponents who responded to this provided, a brick of documentation for their project running many hundreds of pages. But the person leading the request for proposals also requested that every one of the proponents include a RETScreen analysis. And I found that I skipped reading the documentation because it was just, I would get lost in it. There was just too much there. Each proponent was using a different methodology to look at their project. And I would go right to the RETScreen analysis. And very quickly, I would get a sense, okay, this is what their project is. Why are these parameters the way they are? And then I would go and look. That would help me formulate questions that I could then investigate by looking at their documentation. Much more helpful than trying to get a sense of what their project was from the large amount of documentation they provided. So another useful role for RETScreen. So let's demonstrate this for a roughly 100 megawatt wind farm that we're assuming is going to be built within the next 5 years near Merritt, British Columbia, Canada. So this is on the west coast of Canada, or I shouldn't say the west coast. It's the westernmost province of Canada, but a little bit interior. Because it's being built in the next 5 years, it's going to use, turbines of modern vintage. So we can assume 5 to 7 megawatts probably. And this is part of a request for proposals from the utility, who are going to be offering a power purchase agreement for 30 years. And that's significant because, the utility is a provincially associated utility. It's you can be very confident that you will be earning what they have agreed to pay you over a 30-year period. That has consequences for financing, right? Banks likes to see that you have someone who's very reliable buying your electricity. That's good. But it also means you're in competition with other people who are going to be bidding in this PPA. And we are going to assume that you can expect your competitors to be coming in with proposals where they're going to be asking for around 7.5 cents a kilowatt hour. So you want to see if you're going to be in the ballpark with your project. And we can look at this from two different perspectives. One, we can imagine you're the proponent investigating options. Is this this proposed site, is it a good site? And for them, they might be looking at, okay, given this site, what must each kilowatt hour of wind farm output earn in order to achieve a 12% internal rate of return on equity? So they know that their equity investors want to have a 12% internal rate of return. So what would they have to charge for each kilowatt hour of output to achieve that return? And then they can compare that with the 7.5 cents a kilowatt hour that they're expecting, to be more or less where their competitors are coming in. That's one perspective. A second perspective might be, say, a local government in the area investigating whether proponents' claims are reasonable. And in the case of, interior British Columbia, this might be a First Nations group who has a proponent coming to them and saying, hey, we've got a great project we want to partner with you on. You might want to have a good understanding of what that proponent's project looks like. And you can do a RETScreen analysis to investigate that. So for example, you might be trying to negotiate with the proponent to get community benefits out of this project. To say, listen, we think that, because of the inconvenience of this project, because of the impacts it may have locally, we should have compensation both during construction and on an ongoing basis. And you could use RETScreen to kind of bolster your claim that this is something that the proponent could afford. So these are the two perspectives we're going to look at. Now, what we need to do to run the energy model is we need to have a few pieces of information. And the first of these is a turbine power curve. So a turbine power curve is an indication of how much power our turbine produces given a particular instantaneous wind speed. So if at a given point in time, the wind is blowing at, say, 7 meters per second, we would look here for this particular turbine and see that this particular turbine was going to be putting out around 2.5 megawatts at that point in time. This is for a particular turbine, obviously. It's called an Enercon E175. I picked it for 2 reasons, or 3 reasons, really. One, because it's a 6 megawatt turbine that's current vintage. You can go to Enercon and buy one of these turbines right now. It's all listed on their website. So it's a potentially a turbine that might be used in such a project as this that's being done in the next 5 years. The second reason I picked it is because it's got an IEC rating or class rating of type 2. So what does that mean? If you look up online, thought I had something here, yes. IEC wind classes, you see that turbines have to be tailored to the wind resource they're being used in. So if you have a very strong wind resource, you need to have turbines that are going to tolerate those wind speeds, not get damaged. If you have a less good wind speed, less strong wind resource, you can maybe build it to not be able to survive the same high wind speeds, but such that it will generate more power at low wind speeds. So the IEC wind classes essentially indicate whether a turbine is appropriate for a given wind regime or not. And we're talking about a class 2 turbine, which means that the average annual wind speed at the height of the hub, meaning the center of the turbine rotor, is 8.5 meters per second or less. And that's what I'm expecting to find at this site. So this is one of the reasons I picked this turbine. So we see that here. The third reason I picked this turbine is because I could actually get the power curve for it. Very easily online, you can find this information. So that was the third reason. So now we have this power curve. What else do we need? Well, we need an accurate estimate of the wind resource at our site. And this is particularly critical for wind farms because a small error in the estimate of the wind speed will lead to a big error in the production estimate. And we can see that simply by looking at this power curve, right? If we think that the wind speed is 7 meters per second, but it's actually 6 meters per second, which isn't, a huge difference, the power output of the turbine drops from 2.5 megawatts down to 1.5 megawatts, basically, just because we've got a 1 meter per second error in our wind speed measurement. So if we've got a poor estimate of our wind resource, we're likely to have a poor estimate of the energy production. And that means we may really fall short of profitability. So we'll build a $200 million project and discover, oops, we didn't have the wind speed we thought we had. And then investors are not going to be earning their return and they're going to be very unhappy. So that's the first concern. The second concern we have is the wind resource changes significantly from one location to the next. So we have to, have data from our site one way or the other. Either we can get that from models or we can get that from instrumentation on site, but we need to have site-specific information. And the third thing is we need to have an estimate of the wind speed for every hour of the year. And I used hour because, wind speeds don't necessarily change that much from hour to hour. But, if they were, then maybe I'd have to say for every 15-minute period of the year. And why is that? It's because if we go back and look at this turbine power curve, we see that it's not a linear relationship between power and wind speed. That is, this is not a straight line. If it was a straight line, we could take the average wind speed measured over the course of the year and simply read off the power for that average wind speed. Say the average wind speed was 8 meters per second. We could just read off this that, hey, that's going to generate about 3.5 megawatts every hour of the year on average, right? However, because this is not a linear curve, that doesn't work. And the easiest way to see that is to look at a limit case. Imagine the average wind speed was 2 meters per second. Looking at this curve, you would say, well, if we believe that we can use this just with the average wind speed, then that would indicate zero power over the course of the entire year. But clearly an average wind speed of 2 meters per second means that there's going to be times when it's, 3, 4, 5 meters per second. So during those times, your turbine will be generating power. So clearly this approach doesn't work of using this with an average wind speed. It only works with instantaneous wind speeds. So what we need to do is we need to have a measurement of the wind speed for every hour of the year, and then read for that hour what the power output of the turbine was going to be, and just sum it up over all hours. And we could do that by just having a record of all the hours in the year and their wind speeds, but that would be 8,760 values, right? That's the number of hours in a year. Maybe an easier way to do it would be to have a histogram saying how many hours per year do we expect wind speeds of 1 meter per second? How many hours per year do we expect at 2, et cetera, right? So then if we've got 30 wind speeds, say from 0 to 30 meters per second, then we only need 30 values. But we can approximate that using a probability distribution, right? So there's this function called the Weibull function, which essentially allows us using two numbers to generate an estimate of how many hours per year the wind is blowing at every wind speed. And we have, for this example here, we're seeing the wind speed along the horizontal axis and the probability or the frequency with which that wind speed occurs over the course of the year on the vertical axis. And the reason we're seeing all these different curves in different colors is because the Weibull distribution is a 2-parameter distribution, meaning we can fix the average wind speed. So all these variants have the same average wind speed of 6 meters per second, but we can vary the shape, which is described by this parameter k. So in orange, you have k equal 2, and that's this curve. It has an average wind speed of 6 meters per second, but it tends to have more low wind speeds. And then also it tends to have, a fairly long tail where there's occasional high wind speeds. In contrast to that, with a higher shape factor, you have a much tighter distribution around the average. So the distribution of wind speeds kind of approximates a histogram. And if we plug this in, or we use this to estimate the number of hours per year that we have each wind speed, and then we combine that with the turbine power curve, we can come up with an estimate of the electricity production over the course of the year. And that's the approach that RETScreen is going to use. We don't actually have to do that. RETScreen does that. But this is the information we're going to have to provide to RETScreen. So let's do that then. We are going to start a blank feasibility analysis here. And the first step will be to choose the location. And the location I will pick here is Merritt, BC. I'll start by searching for Merritt, BC. And when I do that, I see that there's this option popping up. So I double click on that and it takes me to Merritt, and I can zoom out here and see where I'm located. I'll zoom out way out so you can see that we're over on the western side of Canada, right? There's Vancouver, BC, there's Calgary, there's Seattle, Washington. And we see there's two thumbtacks here. One thumbtack with a little building on it is where we're proposing to site our project. The other thumbtack is the nearest location for climate data, or at least the currently selected location for climate data, which if we leave RETScreen alone, will always be the nearest one. So I'm going to zoom in a bit and just take a closer look. If I can see that if I move this around, that climate thumbtack moves around to different locations based on what's the nearest location. So I am going to, let's see, I'm going to zoom in a bit more, and I'm going to pick a location right here. I'm going to imagine that our project is situated somewhere around here. We can adjust that later on. And we see that the nearest site for climate data is actually 60 kilometers away, right? That's pretty far. If we zoom out, we see that it's down here in Princeton. So we've got climate data from here, but our site is somewhere around here. And there's 60 kilometers separating the two. That's as good as we can do for now. So I'm going to accept that and paste that in. You'll see this data updates here. This, as I mentioned, is the climate data. For a wind farm, we're particularly interested in a few different parameters. The first is the elevation. We have the elevation for a climate data location, which is 700 meters above sea level, and for a facility location, which is where we dropped that thumbtack, which is about 1,100 meters above sea level. And you'll see that that's going to be significant. We also have the wind speed, which we're obviously going to need. However, this wind speed is from Princeton, which is 60 kilometers away from our site. Clearly, we shouldn't rely on, at least without having very carefully analyzed it, wind speed information from 60 kilometers away. So this is not helpful for us. We're going to need a better estimate of the wind speed than this, particularly because I can see that this is measured 10 meters off the ground. And we know that wind typically increases, the speed increases as we get higher and higher off the ground. So with a wind turbine that's 162 meter hub height, and I don't think I mentioned that, but if we look back at our power curve, we see this is a 6 megawatt turbine with 162 meter hub height, meaning the center of the rotor is 162 meters off the ground. That's, much higher than 10 meters. So to use a 10 meter estimate with a turbine that's 162 meters and hub height is asking for trouble. I should also mention there's a 175 meter rotor diameter and 24,000 square meter swept area. That is, the rotor sweeps out 24,000 square meters. It's an absolutely huge device, right? So this wind speed isn't going to be terribly helpful for us, but what may be helpful is the air temperature and the atmospheric pressure. Why? Because these don't change so much from one location to the next as wind speed does, but we do need them for estimating the power output of our turbine. Why? Because the kinetic energy of the wind that's available in the wind is a linear function of its mass, right? And what do we mean by mass? We mean the density of the air. And the density is determined by the atmospheric pressure. That is how much the air above our location is pressing down on us, and the air temperature. That is how cold it is. And this site is a little bit colder than the standard test conditions of 15 degrees Celsius, which are used with a turbine to estimate the power output of a turbine. So the air is going to be more dense than in that test, and that'll tend to increase its output. This atmospheric pressure is lower than the atmospheric pressure at sea level, which is the assumption used when you're evaluating standard test conditions for a turbine. Why? Because we are at 1,093 meters above sea level, according to this. Now, one thing you have to be careful about is this air temperature is a ground measurement. So there's a single point in the ground where these measurements are being taken. This atmospheric pressure is from a satellite instrument. And if we look at HELP, we can see that the satellite resolves not a single location, but an area. And in this area is actually about 50 kilometers by 50 kilometers. It's half a degree of latitude and longitude. So at this, at mid latitudes, it'll be around 50 by 50 kilometers. So it's seeing a whole area. And over that area, this is the atmospheric pressure that it estimates. But this is for an area, and this is for a point on the ground. So we have that information. Now we just have to configure this for a wind farm. We see that we've got feasibility selected here. We don't have a performance analysis selected, so that's fine. We do want to use wind turbines. So I can search here for wind turbine here and select wind turbine. For the description, I'm going to put in utility scale project. That way, if I ever put it in a portfolio of projects, I can compare it to other utility scale projects by searching for this key. These gray cells here, I'm not required to put anything in, but I can choose to put something in. And then if I share this with other people, they'll know who I am and who I did this for. So this is prepared for a webinar, and it's prepared by Michael. And if I really wanted to be fancy, I could click here and put in my details, and that way, someone could find me. And then I can give it a facility name, which is maybe Merit Wind. Put in the address if I want. Whoops, Merit should be spelled correct. And I could put that in. I'm not too concerned about this benchmark, so I'm actually going to make it go away. So I'm going to click here to hide the benchmark. It's not going to be a part of my analysis. Next, I go to the energy page here. First, I'm going to click on electricity and fuels. I see there's natural gas there. Not worried about that. Here is the electricity export rate. This is what I'm going to get paid per kilowatt hour of electricity output. This is what I'm trying to determine. What do I need to get paid to earn 12% internal rate of return on equity, right? So I'm just going to leave that at the default value for now, and I'm going to come back to it and change it to achieve a 12% internal rate of return once I've specified the other elements of my project. Now I need to add in step 2 here, a wind farm. So I click on wind turbine here, and I'm going to call this wind farm. Let's change the name, and you see I've added a wind farm now. And I have 3 different levels of analysis. I'm going to start with the simplest level of analysis. And here I say I have a project that's going to be roughly 100 megawatts, right? That comes from this slide where we said it's going to be 100 megawatts. And I am now going to specify the capacity factor. You might recall I defined the capacity factor. It's the average output of our turbine, of our wind farm, expressed as a percentage of the nameplate power capacity. So maybe I look into this and I find out that, many wind farms that are being built in North America have capacity factors around 45% these days. So maybe I think, I'll start off with that. I'll put in 45% here. And then I put in the initial costs and I say, really, I don't know how much these cost. So I'm going to use this this cost database here. I click here and this table comes up that tells me for projects of a scale of around 100 megawatts per kilowatt, I can expect to pay around $2,100 Canadian per kilowatt. Now, the reason it's important to specify that that's for a 100 megawatt project, because there's obviously economies of scale. The bigger your project, the less you pay per kilowatt. So I'm going to use that estimate. Now, if you had a better estimate, you're not obliged to use RETScreen's cost database. You can write in whatever value you think is appropriate. But if you don't have that, this can be your first estimate here. Now here for the O&M cost, so that's for the initial costs, $210 million to build this project. For the O&M costs, you can click here and you can estimate for a project of this scale, how much does it cost to keep the project operating in a good state of maintenance per kilowatt per year. And the estimate provided here is 55 Canadian dollars per kilowatt per year. Once again, you're not obliged to use that estimate. If you think that's too high, put in your best estimate. But if you don't have an estimate, then that gives us 5.5 million per year. So we see that we are now going to be generating electricity export revenue of about $40 million per year, $41 million per year. Out of that, we have to pay 5.5 million for O&M. And to build the thing, we had to pay 210 million. And at least these 2 figures are summarized once again on the cost page, right? They're just carried over if I have a level 1 analysis. So my initial costs and my annual costs are here. I can go to the emission page, and using this level 1 analysis here, I see that like Quebec, BC, which also makes heavy use of hydro, has a very low average emissions factor. It generates power fairly cleanly. So putting wind on this grid won't necessarily reduce the output from dirty fossil fuel generation much. And as a consequence, we have a very low gross annual GHG emissions reduction associated with this project. It almost certainly does not make sense to try and monetize this. It'd be more hassle than it's worth. But if we did think we could do that, we could put a value here for the GHG emissions reductions. Very quickly, we go to the finance page. For simplicity's sake, I'm going to leave this on level 1 here. I'm just going to adjust these figures here. The inflation rate is, let's say, 2.5%. So this is going to be applied not just to my O&M costs over the lifetime of the project, but also my electricity revenues. For the project life, I think these turbines are going to last 25 years. So the PPA is 30 years, the power purchase agreement is 30 years, but the equipment, maybe we can expect it to last 25 years. And for the debt ratio, I'm going to be a little bit conservative here and say 50% debt ratio, meaning half of the project is the initial cost of the project are being provided by a financing institution, and half of it is being provided by our equity investors. Because we probably are going to have, we are going to have a PPA, which means this is a fairly secure project. Banks will probably be pretty interested, or other lending institutions will be pretty interested in working with us. We probably can have a fairly low debt interest rate. So I'm going to start out assuming 5%. But if you think these assumptions are incorrect, you can put in what you think is right. And then I'm going to leave the debt term at 15 years, meaning the 50% of the initial $210 million that cost to build this project that comes from the banks needs to be paid back with 5% interest over 15 years. And based on that, we can see that under the current assumptions, we have a really profitable project, 28.1% internal rate of return on equity. So we're only targeting 12% internal rate of return on equity. So we could afford to reduce what we're charging per kilowatt hour and still achieve 12% internal rate of return and have a much more competitive project. That is, it's great to receive 28% internal rate of return, but if you're doing that by charging 10 cents a kilowatt hour and your competitors are going to be proposing projects at 7.5 cents a kilowatt hour, you're not going to win your request for proposals. So you're not going to get to do a project. So you got to see, can we get the price down to something that's competitive with 7.5 cents a kilowatt hour, for example? So going back here, what I'm going to do is I'm going to open this dashboard functionality, and I'm going to look at the financial viability parameters here, namely the pre-tax IRR on equity, the return to our equity investors, while I change the electricity rate. So I know that 10 cents a kilowatt hour earns 28%, which is more than we need. So maybe I can go, say, with half that, 5 cents a kilowatt hour. And we see, no, that's actually, I've gone too far. I won't be earning the return that's our investors are insisting upon. So perhaps I can go like up to 6 cents a kilowatt hour here. When I do that, I see, yeah, that's about right, right? So I need to charge about 6 cents a kilowatt hour under this set of assumptions to achieve a 12% internal rate of return here. Yeah. So that's kind of interesting. Let's go and look at the risk analysis here. And in particular, I want to go down to the risk analysis here and look at the pre-tax IRR on equity, because we want to achieve a 12% pre-tax IRR on equity. So that's what I'm going to look at here. And I'm going to see what are the parameters that have the biggest impact on our project. And I see by this being the longest bar, the single parameter that has the biggest impact on my pre-tax IRR appears to be the amount of electricity that's being exported to the grid. So the amount of generation is actually the most critical parameter in this analysis. So let's go back to the energy page. How did we estimate that? Well, let's see. We did a level 1 analysis where basically, out of looking at other wind farms that achieve a 45% capacity factor, I assumed that we would achieve a 45% capacity factor. And that's a pretty weak argument, right? We really should assess whether the conditions at our site are capable of providing us with a capacity factor of 45%. So rather than specifying the capacity factor, I'd like to input to RETScreen the wind resource and the turbine power curve and have it calculate the capacity factor. And I can do that on a level 2 analysis here. So in a level 2 analysis, I'm going to start off by specifying the wind resource here. And one option would be to get the data from the climate database here. But I can see that, the climate database has this estimate from Princeton, 60 kilometers away, measured at 10 meters above the ground, and my turbine's at 162 meters above the ground hub height. So this is not acceptable. This is not going to be a good estimate. Fortunately, if I look here, there's this little global wind atlas button. I can click on that and I can get a global wind atlas that gives wind speeds pretty much everywhere on the planet, other than in the middle of the ocean. And I can search here for Merritt, BC, and click on that, and it takes me right to Merritt, BC. And I will zoom out a bit here. Oops, first I'm going to get rid of it. I'm going to zoom out a bit. So I can see where I am with respect to other locations. Actually, I wish this would go away. Yeah, there we go. So I can see, you know, here is Merritt here. I've accidentally clicked over here. I didn't want that. There's Kelowna. Our site is somewhere in this area here. So I'll zoom into this area a bit. Now, right now, what this is showing me in, according to the colors, is the mean wind speed at the sites. And we see that as I move over these areas, the mean wind speed is indicated here. And this is the mean wind speed at a given height. And right now we're looking at 100 meters above the ground. And our turbine has a hub height of 162. So I'd probably be better off picking 150 here. And then I get some different estimates. So this is one way this is really useful. It can give me some estimates of the wind speed. And you'll see that it's high resolution, right? This is, you know, over the area of several hundred meters, it catches changes in the potential wind speed. This is coming from a model, so it's not perfectly accurate, but at least it's specific to our site. Another thing that's interesting is I can look at the layers here, and I can get it to include like roads, right? So I can see where roads are. If I take away the this measurement, sorry. So we can see roads going through these areas, but we can also include the electricity grid. That's really important, right? You can build a great wind farm, but if there isn't transmission lines to get it to population centers, it's not much good for you. But I can see I've got like red lines here are greater than 500 kilovolt transmission lines in this area. So this could potentially be a great area to build a wind farm, right? We got transmission capacity right on site. And when I look at the wind speed, this area here has pretty good wind speed. Right? So I'm going to select this area here, just guessing that we could build a farm. And I have not looked to see whether this is where potential farm is being sited. I'm just making this up. I select this area, and the wind atlas for this particular area gives me the wind resource. It tells me that at 150 meters above the ground, the average wind speed is 8.14 meters per second. And this is over this area. These are the most windy sites, the 10% best sites in this entire 171 square kilometer area. But, you know, we could probably site our turbines at these best sites. You don't choose the worst sites, you choose the best sites. So this is probably a reasonable estimate of the wind speed, 150 meters off the ground at sites in this area. So this is, now we're cooking with gas. We can go back to RETScreen and say, yeah, I've got a wind speed estimate. It's not 1.3 meters per second, 10 meters off the ground. It's 8.14 meters per second, 150 meters off the ground. That's a much better estimate of our wind resource. I'm going to skip the wind shear exponent for a moment here. The next thing we have to specify is the air temperature and the atmospheric pressure. These dictate the density of the air, which have an impact also on the wind resource. And one option would be simply to copy the data over from the climate database, and that would be okay. But I got to be a little bit careful because the air temperature here is coming from Princeton, right? It says that, Princeton. And when I look at the climate data location, Princeton, it's 700 meters off the ground, okay? And this here is indicating that where we drop that thumbtack is 1,100 meters above sea level. I said 700 meters above the ground. I mean above sea level. This is 1,100 meters above sea level. And we can confirm that looking at the orography here. So I click on this layer, and I see the color now represents the elevation above sea level. And I see, you know, at the highest sites here, I'm at maybe 1,400, 1,500 meters above sea level. But most of this area, I'm around 1,100 meters above sea level. So yeah, I'm, you know, well above sea level. So there's less air pressing down on me. So it's less dense, the air. And what I could do is I could say, you know, when I add in the 162 meters of height on the tower of my turbine, I'm probably going to be around 1,400 meters above sea level for most of my turbines at hub height. So I can go to this air pressure at altitude calculator, or any air pressure at altitude calculator, and say, you know, if the pressure at sea level is 101 kilopascals, which it typically is, and the temperature is 15 degrees, what is it at 1,400 meters above sea level? And I hit calculate, and it says it's about 86 kilopascals. So I could go then back to the energy page and put in 86 kilopascals here for the atmospheric pressure. It just so happens that if I had used the climate data location, climate data from RETScreen, I would concur with that almost perfectly because it said it's at 1,100 meters. So, you know, it's getting more or less the same types of elevation. For the air temperature, though, you know, I started off talking about the air temperature. I skipped to the atmospheric pressure. I apologize for that. This is at 700 meters in Princeton, 700 meters above sea level. We're going to be at maybe 1,400 meters above sea level, right? 700 meters higher. And as you get higher, temperatures drop about 6 degrees Celsius per 1,000 meters of elevation gain. So going up 700 meters, you know, we might be decreasing the temperature by about 4 degrees. So maybe here on the energy page, rather than putting in 6.3, I'll put in something like 2 degrees Celsius here as the average air temperature over the course of the year. So now we have most of our wind resource in there. The next thing we want to get in is the power curve for our turbine. And we can consult RETScreen's product database here to get a power curve. And I can look for an Enercon power curve here. And if I look here, I see that the E175 turbine that I wanted to use isn't here. So maybe I can pick a different turbine. If I pick this one, it's a 3 megawatt turbine, but the power curve is available for this one. So how about I use this one for now? So I click on that, and you'll see that all these cells get filled out. So we have a 3 megawatt turbine. It's got a hub height of 135 meters. And here is the power curve. So that's great. However, I don't need one turbine. I really want about 33 turbines in order to get 100 megawatts, right? And the other thing is, if I look, I'm not actually, you know, RETScreen isn't calculating anything right now. And one reason for that is because I haven't filled out all the parameters. And one I'm missing is the wind shear exponent. And the wind shear exponent is what your RETScreen uses to adjust this wind speed measurement at 150 meters to the equivalent wind speed at 135 meters. So to pick a good wind shear exponent, I can click on help here, and I'll see a definition of this and then a suggestion that a value of 0.14 is a good first approximation when the site characteristics are yet to be determined. So I'm going to put that in. And when I do that, I see that RETScreen estimates that although I've got a 8.14 meter per second measurement at 150 meters, at 135 meters, which is the hub height for these turbines, it's 8 meters per second. So the last thing that we've got here that's interesting is there's an energy curve here. So what's the energy curve? Well, that's going back to the presentation. That's this thing, right? This is, whoops. This is the energy curve. And we've given RETScreen the average wind speed, and the K factor, the shape factor, is the other parameter that determines the shape here. And right now we've got this set at standard, which means a K factor of 2. It corresponds to the orange line here, right? So that's our assumption for the distribution of wind speeds. And based on that, RETScreen can calculate this energy curve. So the power curve is for an instantaneous wind speed of 10, say. This is the power output of the turbine. The energy curve is for an annual average wind speed of 10 meters per second. This is how much energy a single turbine would produce before losses and adjustments. So we can check that, right? We can look here. We see that we have at the hub height 8 meters per second here. So we would expect a turbine to put out on a course of the year just under 12 gigawatt hours. And if we go to the bottom here, we can click under other information, and we can see that that's precisely what we find. Per turbine, we're getting unadjusted 12 gigawatt hours. Now, of course, we have to adjust that based on the pressure. Here's the pressure reduction because we're up 1,400 meters. We reduce the output of the turbine. And the temperature coefficient. Because it's fairly cool at this site, we increase the density of the air. So there's an improvement in the performance due to that. And overall, the combination of those two effects is a gross energy production of 10.5 gigawatt hours per turbine. However, that doesn't take into account other losses that might occur. So what are the other losses? Well, they're accounted for here. The first of these is array losses. Array losses reflect the fact that we're not just installing a single turbine, we're installing multiple turbines. And if the turbines are close enough together, then an upstream wind turbine robs a downstream wind turbine of some wind energy, right? The wind speed slows down after it passes through a turbine. It doesn't have as much energy to impart to the downstream wind turbine. So RETScreen's help can help us with this. It says, 8 to 10 turbines should keep losses below 5%. We've got more turbines than that, but I'm still going to go with 5%. Why? Because when I go back to make this go away. There we go. When I go back to this, I see that my site here is kind of north, along an axis that runs from northwest to southeast. And that's basically at right angles to the dominant wind direction at this site. So I put a kind of line of turbines along here and maybe a line of turbines far away along here. And I'm really not going to have a lot of array losses to contend with. That's my speculation. Of course, you'd have to use a detailed engineering analysis tool to verify that, but it looks promising based on the dominant wind direction here. Oops, did not want that one. I wanted to look at this. Yes, 5%. So that's how I came with 5%. For airfoil losses, this reflects the fact that dirt on the turbine blades, bugs that accumulate on the leading edge of the turbine blade, or ice or wet snow that accumulates reduces the aerodynamic efficiency of the blades. And so this is a loss factor. And typical values range from 1 to 10%. I'm going to assume 4% here. And for miscellaneous losses, once again, going to help. It sees typically 2 to 6%. I'm going to assume 3%. Now, all of these can be argued. And, detailed engineering analysis would maybe adjust these figures. However, what matters is that the combination of all three be reasonable. And we're now at, combined losses about 12%, which is fairly typical for wind farms. The reason I went a little high on airfoil losses is because it's a fairly cold site. You shouldn't have too much rime icing, which is particularly problematic because it's not near open water, and it's not that cold, but you could have some wet snow buildup on this. The last thing here is the availability. That's a measure of what percentage of the time will your turbines be available to operate should the wind be sufficient to operate them. So it's not saying when I put in a figure like, say, 97%, that the turbines are actually operating 97% of the time. It's just saying if there is sufficient wind, 97% of the times the turbines are ready to operate when the wind blows. Now, based on that, I've got a capacity factor now, right? 34.4%. So that's much different than the 45% that I assumed initially. And this will have a big impact on our project. If I go back here to put in the same numbers that I had before for the initial and operating costs, and then go back to the finance page, I see I'm no longer at a 12% internal rate of return. I would have to, quite significantly adjust the price I'm being paid for electricity here. So for instance, if I want to have a 12% internal rate of return, maybe I need to get paid something like 9 cents a kilowatt hour. I'll try that figure. Well, that's too far. So maybe it's more something like 8 with this particular turbine. Yeah, so with this particular turbine, that looks more or less reasonable. Now I could do other things as well, but really what I really should do is say, listen, the turbine makes a big difference. We really should get the power curve into this analysis. So going back to here, what can I do to get the power curve into my analysis? There's no magic way to get these automatically into RETScreen if they're not in the database, but you can simply enter these numbers manually, copying them off the power curve. It's not as much work as you think it might be. There's really only about a dozen numbers you have to copy over, and it takes a few minutes. So that's not really a big deal. But rather than make you enter these, I'm just going to switch to another presentation or another RETScreen file, which I prepared in advance, which includes these numbers. You can see there's the power curve right there for the 6 megawatt turbine. And that way you're not bored with me entering numbers here. I have to put in the wind speed, which was 8.14 meters per second at 150 meters. The turbine's at 162 meters. I need to have 16 turbines to make a roughly 100 megawatt wind farm. It's only 96 megawatts, but that's okay. You can see that at 162 meters, the wind speed is 8.2 meters per second. Here, this results in a capacity factor now of 41%. And this is a turbine that's, of recent vintage, designed to operate well with more moderate wind speeds. So that's how we achieve the better capacity factor with this turbine. So because of this better capacity factor, we are now at 16.8%. I can once again adjust the electricity and fuels to achieve 12%. So I can lower this maybe to something like 7 cents a kilowatt hour. Even that's too high, right? So maybe about 6.8 cents a kilowatt hour. Still too high, interesting. Yeah, 6.6 cents a kilowatt hour here. So that kind of shows how you can refine your analysis from the perspective of someone who's trying to negotiate with the proponent and say, I'm representing the local community, and I think you should provide us with some benefits for this project. You could, do this analysis and then say, listen, if we had to add in some additional costs here, and the additional costs were for, say, community benefits that we're being paid on an ongoing basis to, compensate the community for any inconvenience, additional traffic, the site of turbines locally, perhaps environmental impacts. There may be changes to animal behavior in these areas that could be very important for First Nations groups, for example. Let's say you wanted to argue with the proponent that they should, give you your community $1 million per year here. And you wanted to see, whether their project could support that, or whether that would have too big an impact on the financial viability of the project such that it would eliminate it from contention in the request for proposals. And maybe you even wanted to say, hey, I think we should get some upfront community benefits. So we've got both upfront community benefits and ongoing community benefits. And we're going to ask for $5 million upfront. Yes, and $1 million each year of the project's in operation. What does that do to the project financial viability? Going back to the finance page, it hasn't made a huge difference, right? We're at 10.6%. We were at 12. So once again, we can get the dashboard out, go to the energy page, and look at the impact on the cost of what we should be charging for electricity. And you might find that it's like 7.8. Well, even that's too high. 7 cents a kilowatt hour. Yeah. So this would, if you were in the community, bolster your claim that in fact the proponent could afford to do this project, pay significant community benefits, and still achieve a price, 7 cents a kilowatt hour, that achieved the equity 12% internal rate of return that your equity investors were seeking. And this price is below the 7.5 cents a kilowatt hour that you're expecting your competitors to bid at. So you could, do this analysis and then bring it to a meeting with the proponent and say, yeah, I think you can pay us. And, they can then say, no, we can't afford that. But then you can say, well, where in my analysis have I gone wrong? And you can at least have a basis for your negotiation. There were some other things I could show you here, but I think I should open this up for questions. Any questions or comments here? And I apologize again for the loss of audio there for a bit. No questions? Anything you'd like to see or that didn't make sense? Can I confirm you're still there? Anyone still there?
Yeah, Bueller's here.
All right. So just no questions. Okay. All right then. Well, I mean, that's an overview of the use of the RETScreen software to do a feasibility study for a wind farm. It can also be used for performance analysis and benchmarking, as we saw, but the focus here was on feasibility or pre-feasibility analysis. If you have a question, you can, send it to me or send it to RETScreen either. Going back to the presentation here, in terms of follow-up, for those of you who attended the presentation, I'll send you by email a 1-month subscription key unlocking RETScreen's professional mode. So if you don't currently have subscription, this will give you 1 month of the full capabilities of the software. And the recording of this webinar will be made available on YouTube. So I'll send a link for that as well if you care to review it. Any final thoughts? No? Okay. Thanks very much for attending, and I hope this was of some use to you.
Thank you, Michael.
Thank you. Bye-bye.